All right, so we're going to ask another seemingly stupid question. How big is big? Is that big? Last time we noted the sample average usually has a normal distribution. Asterisk next to the word usually. If you talk to mathematicians, they can rig up cases where it's not going to be true. But for a lot of cases, it's true. The sample average usually has a normal distribution. But we still have sampling variation. There's always going to be some difference from the true mean. But the question is that big? Is that a big difference? How do we figure out how big is a big difference? How big does it have to be in order to be called big? We just saw some of this in our lab in class, trying to load the dice and distinguish, produce a big difference from a fair dice. So from the example in class, we can represent this as a tree diagram. First roll, we can have 6 different outcomes of the dice, but to keep the picture simple, let's collapse that to concentrate on either the dice comes out as 6 or it comes out as some other number. That way each level of the tree has just 2 branches. You roll the dice, either you get a 6 or you get a not 6. The next roll, you get either a 6 or not 6, and you just keep on doing that. I've shown, the first 3 rolls in the table and highlighted the ones where you get 2 or 3 6 values. That'd be one sort of candidate decision rule or testing protocol to say, well, the dice is loaded if, when I roll it 3 times, 2 out of 3 times come out 6, or 3 out of 3 times come out 6. Now you'd want to figure out what is the probability of each of those happening if the dice were fair. This is all thinking like a statistician, which, seems kind of thinking upside down, I gotta admit. It's a little weird because we say, well, what if there were actually no difference? What if there's nothing going on? What if the dice are not loaded? Actually, they're completely fair. What if? Right, so generally we'd say a big difference is evidence that there's something really there. And a small difference is not going to be much evidence. So we'll come back again later that failing to find evidence is not the same as evidence that there's nothing there. Absence of evidence is not evidence of absence. Those statements are a little bit different. Regardless, step 1 is measure, is there a big difference? And then ask, okay, how big is big? The law of large numbers makes the assertion that the sample mean is going to have a normal distribution, with the mean as mu, the true value, and the standard error is the standard deviation divided by the square root of n. Recall when we were looking at our sample of poles, if I went from 10 to 100 to 1,000 to 10,000, the variation got a lot smaller. That's because we're dividing by the square root of n. The fact that it's 1 over the square root gives me that diminishing marginal returns aspect. The formula for the standard deviation divides by square root of n minus 1, which might seem a little weird since I'm dividing by square root of minus n minus 1 and then divide again by square root of n. But yes, that's actually what we want to be doing. We often standardize the test statistic by taking the estimate, x bar, divide by its standard error, which is s over the square root of n, assuming the null hypothesis is mu ought to be 0. The test statistic z would be expected to have a mean of 0 and a standard deviation of 1. The mean is unbiased, so as n gets larger and larger, then s divided by square root of n is going to get smaller and smaller. So as n grows, we would expect to get closer and closer to the true value. Now, where did this formula come from? It's actually pretty easy to derive just from our previous assertions about linear combinations. If z is x plus y, then mu z is going to be equal to mu x plus mu y. And the standard deviation of z is the standard error of x plus the standard error of y plus twice the covariance, all over the square root. And we recall the other rules for linear combinations. For n equal 2, x bar is just a half of x1 plus a half of x2. Mean is going to be half of the mean of x1 plus half the mean of x2. If those are the same, then that gives us mean of x. Expected value of the sample mean is going to be the true mean value. Next, look at the standard error formula. The standard error of the mean will be a half squared plus sigma squared x1 plus a half squared sigma squared x2 plus a bunch of terms of the covariance, but assume the covariance terms drop because the covariance should be 0. Take out the half, do a little simplification, and you find exactly our formula, 1 over root 2 times the standard deviation of x. I'll leave it to you as an exercise. Do the case of n equals 3 or n equals 4 or n equals any arbitrarily large number, the formula just checks out. Trust me.